So hello everyone, just like Claudia said, I'm Jenni Kontkanen from CSC IT Center for Science that we have in Finland, and I will present the climate adaptation digital twin. I will start with some motivation. So we all here know that climate change will have severe impacts on human and natural systems during the coming decades. However, regional and local effects of climate change are still highly uncertain. In addition, current climate modeling activities have some limitations regarding how well they can inform climate change adaptation actions. So these limitations include low horizontal resolution of these global climate models, and also the slow process of climate modeling, which doesn't include interactivity with the users of this climate information. And for these reasons, new solutions are needed to inform climate change adaptation efforts and also to assess risks of failed mitigation actions. And because of this, we are developing this climate adaptation digital twin, or climate digital twin, like we call it. And this climate digital twin is a new type of climate information system that can be used to assess impacts of climate change and different adaptation strategies at local and regional levels over multiple decades. And this, our climate digital twin, will include global climate simulations at the unprecedented horizontal resolution. We will also include a very novel approach where the climate model output is streamed to a set of impact models that evaluates impact of climate change on different topics. I will soon explain this in more detail. Climate digital twin will also include quality assessment and uncertainty quantification, which is based on Earth observations, and the whole system will be deployed on 2 European pre-exascale supercomputers. I will tell next more about all these different aspects. And I will start with this streaming idea. So this is illustrated in this schematic here. So on the left-hand side, you can see this. Let's see if the light, okay, you don't see it so well, but on the left-hand side, you can see the 2 climate models that we are utilizing, so IFS VESOM or NEMO and ICON. An output of these climate models is standardized in a form that we call generic state vector. And this generic state vector is then streamed to these different applications. And these now include these different use cases, which can be these impact models, and also an application for quality assessment and uncertainty quantification. Then also at least some fraction of this generic state vector can be stored to destination Earth data lake via this data bridge. Streaming of this climate model output in this standardized form that we call generic state vector enables for the first time for the users to access the full model state as soon as it is available from the climate models. It also can make this system in the future interactive. So this can mean that in the future users could request simulations based on their needs. In addition, it makes this system easily scalable, so we can add there new applications that operate on this generic state vector. Okay, then I will tell a bit more about these 2 Earth system models that we utilize. So they are ICON and IFS VESOM or NEMO, and these are the only European models that are currently able to simulate at 5 kilometer and finer spatial resolution. And now, during this first phase of Destination Earth, we will perform multi-decadal simulations on 5 kilometer global mesh, but we also do work towards finer scales and also perform some simulations with finer resolution. And these performing these high resolution simulations enable smaller scale processes to be described with physics compared to if you have coarser resolution simulations. And this improves the fidelity of these simulations. Also, this high resolution makes it possible to provide local information that is relevant for users who often act locally. It also makes it possible to compare these simulations more directly with observations. This I will talk more soon. This figure here illustrates how with this fine resolution simulations, you can see more detail and structure in the ocean currents than in the coarser resolution simulations. So these are results obtained with this icon model within a NextGEMS project, which is a Horizon 2020 project. Okay, so we have then these high-resolution climate simulations, and we of course want then to validate them with observations. So in the climate digital twin, we perform this quality assessment and uncertainty quantification on this streamed climate simulation data. And for that, we use a selected set of metrics and diagnostics. Something that is very new in our approach in the climate digital twin related to this is that we implement so-called observational operators in the climate digital twin. So this means that we project these simulations into the observation space. And this allows us to directly compare these simulations to observations from remote sensing and in-situ measurements. It also makes it possible for us to monitor the simulations real time, so we detect as soon as possible if there's something wrong with the simulations. Okay, so then we streamed this validated climate simulation data to these different applications that now include these use cases that assess climate change impacts on different topics based on the streamed climate simulation data. So within this climate digital twin project, we have 5 use cases. So we have an energy use case that explores wind energy supply and demand in the future climate. We have a hydrometeorology use case that investigates extreme event statistics. We also have a hydrology use case that is focused on fresh water availability. Then we have an urban use case investigating human heat stress in the future climate. And then we have a fire and carbon use case investigating wildfire risk and emissions in the future. And more information on these climate digital twin use cases will be presented by Sami Niemelä in the, one of the panel discussions later today. Okay, so these climate digital twin simulations require extreme computing power and data handling capabilities. And for this reason, we are using Europe's fastest supercomputers, and we are using them in an effectively way. So we use 2 Euro-HPC pre-exascale systems. Lumi, that is currently in operation in Kajaani in Finland, and Mare Nostrum 5 that will become available in Barcelona in Spain during this year. Computing resources for the climate digital twin are provided by Euro-HPC joint undertaking. And here you can see the picture of Lumi on the left-hand side, and on the right-hand side it's the old system in Barcelona, as the new system is still being built there. So to develop this climate digital twin, we need an international team with a wide range of expertise. So in the climate digital twin team, we have 13 European organizations with expertise in climate modeling, impact assessments, and high-performance computing. So we at CSC, IT Center for Science in Finland, we are leading the climate digital twin contract. We have then 12 other organizations contributing to this. I don't know name all the organizations here, but we have also some other supercomputing centers. We have different research organizations and universities, and also a couple of national weather services. So then I already come to the conclusions. So this climate adaptation digital twin is a new type of climate information system that is based on high-resolution climate simulations, impact modeling, and high-performance computing. This climate digital twin will enable users to access climate information in a new way and also in the future interact with this system. This digital twin can be used to support decision-making on the impacts of climate change and different adaptation strategies. And the first version of this climate digital twin will be developed by April 24, when the first phase of Destination Earth is ending. But the system will be made available to a wider range of users only later during the Destination Earth program. Thank you.